Videos are used to demonstrate the cause of the relativity effect. The images are scientifically accurate, created by POV Ray or Visual Basic software. The time limits for video encourage brevity. Go to the website for more detail. Use the scroll bars for replays and the pause button for time to cogitate. A mental review in bed before sleep always helps. Albert Einstein's theory of special relativity is a product of the 19th century when trains were the fastest mode of travel and video games were unthought of. Today everybody is familiar with the concepts of space travel and warp drives. They are also watching videos and playing 3D video games. This vastly simplifies the process of understanding or grokking relativity. For our purposes, the train is evolved into a spherical space vessel. I will use spherical and cylindrical spacecraft models to develop the theory in 3 dimensions. Einstein used 2 axioms as the basis for his theory, and we will use the same ones. The first is that the speed of light is constant. The second is that the laws of physics are the same in every inertial system, that is, a system which is traveling at a constant speed. Because the speed of light is the same in every direction, a short flash emitted from a point source forms a sphere. The arrows in this video show how the photons travel the same distance in every direction. The sphere is perfect and is stationary in the observer's space. For every observer, the light pulse continues to expand about the point from which it was emitted. The light ring appears to be moving with the observers. If each of 2 vessels emit a pulse of light as they pass each other, the center of both light rings stay at the same point with respect to the observer. In the first video clip, the observer is traveling at the same velocity as the red vessel, and in the second video is traveling with the green vessel. This observation forms the basis for the following discussion. The sphere of light is always stationary with respect to the observer, and neither its shape nor position is affected by the velocity of the vessel. So what happens when a flash of light is emitted at the center of a hollow spherical vessel? To see inside, we need to slice off the sides. The light expands out to the shell and then reflects back to the source at the center. All the photons of a short pulse must reach the shell simultaneously, and then they must reflect back to the source, again arriving there at the same moment. This is what has always been recorded on the spaceship Earth. We must assume that this is also true for every observer in any moving system. The motion of the reflecting surface causes the light to be deflected forward in the same way as a ball is deflected when it hits a moving tennis racket. You can see the difference between the reflections in the 2 vessels. The bunch of photons shown in white reflect back to the source. Now we can convert the videos into diagrams. The light reflects off the sphere back to the source. In a moving sphere, the light travels from F1 to F2. The vertical line where the reflection is occurring moves forward at a constant speed. The higher the velocity of the vessel, the longer it takes for the light to reach F2. Every ray's path length is the same. Therefore, the reflections must lie on an ellipse or ellipsoid, with foci at f1 and f2. The path length is equal to qrs, and the major axis radius a is equal to qr. From the equation for the ellipse, we get the relationship between the time t in the reference system and the time t prime in the moving system. The vessel must also contract in its direction of travel to make the light reflect correctly. The result is the Lorentz transforms. In the contracted ellipse, the radius along the x-axis is reduced, and the result is this equation. Einstein attributed this contraction to the distortions of space-time. The moving sphere is contracted. Inside the sphere, the reflections occur on an elliptical locus. Everyone believes that their own system is not contracted. Time passes more slowly in the other systems. What happens if a vessel is traveling at half the speed of light and launches a photon torpedo at velocity c? The speed should add to 1.5 c. This does not happen. Both torpedoes travel at 1.0 c. The torpedoes from the moving vessel take longer to leave the vessel. It is shorter and at a higher frequency. Here there are 3 moving systems, gold, silver and copper, and 2 light planes. All are moving in the x direction. In the first case, the system is viewed from the point of view of the gold sphere. In the next, it is from the point of view of the silver sphere. In the last, it's from the point of view of the copper system. The reference system is always spherical. The velocity of sphere B viewed from A is the same as A viewed from B. The occupants of each system believe that they are at the center of the universe, and that there isn't any contraction in their own system. From our point of view, the clocks in the moving system show different values along the direction of their motion. According to Einstein's interpretation, an object is contracted in its direction of travel, and its clocks run more slowly than ours. Here the sphere is traveling at constant velocity. Einstein explained the contraction by invoking the idea of the distortion of space and time. He did not give an explanation or mechanism for this distortion. If observers in the moving system view our system, they will see the same effect as we do in theirs. They can see that in our system the length of the paths f1 to r and from r to f2 are not the same. However, both groups of observers stick to their conviction that both of the distances are the same in their own system, and that a sphere is spherical. This illusion occurs because we are unable to measure the absolute time when the light reaches the surface of the sphere. When a clock is moved, it is affected by the same phenomena as we are trying to measure. It runs at a different speed from the reference clock. The result is an illusion. To explain it away, a distortion of space and time was required to make the theory fit the facts, a technique used in pre-Copernican times. The description of the phenomena shows that it is like looking out of a goldfish bowl, or looking through a lens. The universe seems distorted because of the limitations imposed by the behavior of light. Using the time transform, we can find where a particular value of t prime is in the reference frame. From this we get the concept of time planes. These are infinite plane surfaces in the reference frame. These are in the YZ plane. Each represents an instant t prime in the moving frame. The velocity of these time planes is u, equals c squared over v. U ranges from infinity when v equals 0 to c when v equals c. In a stationary system, v is 0 and the planes go to infinity instantaneously. As the speeds get higher, the planes move slower and get closer together. The sphere moves forward, and the time planes accumulate between the reference point and the vessel. These represent time which has not yet passed in the moving vessel. As the vessel accelerates, the time planes become closer together and pass at a lower rate. When it decelerates, the planes spread out and pass faster until, when v equals 0, they have all passed. Time is now the same in both systems. As the vessel accelerates, time passes slower, but time passes faster as it decelerates. The occupants of both systems are the same age. There are a number of paradoxes in special relativity which have never been explained satisfactorily. These are an indication that something is wrong. The most famous paradox is the twins paradox. In the twins paradox there are two twins, cat and dog. Dog travels to a distant star and then returns while cat rests at home. The argument is made that dog is younger than cat when dog returns. This video shows the readings on the clocks. As dog travels away, the difference between dogs and cats' clocks is negative, but on arrival it is reduced to 0. On the return trip, dog's clock gets ahead of cat's, but when they meet again, the difference has again returned to 0. At any time that cat and dog are traveling at the same speed, there is no difference between their clocks. Their ages are the same, but at one point on the trip, dog was 64 years older than cat. If he died at that age, was he resurrected? The previous description is mathematically correct. This is verified as shown in the graphs of acceleration, velocity, distance, and time. These curves were generated using computer numerical methods. In this case, the acceleration profile is a cosine to permit a simple check of the integration. The program used also permits random walk type profiles, as shown, and produces the same final results. Both the time planes and the computer analysis show that whenever the moving vehicle matches its speed with the reference observer, time in both systems becomes the same. When the twins reunite, they are the same age. The acceleration is not a factor in this analysis. The only factors are velocity and position. In the popular solution, the time equation has been manipulated by setting the distance term, x, to equal vt. This only works if the velocity does not change and x starts at 0. The result is an oversimplification. From the graph, the time in both systems during the initial acceleration is little different. The twins paradox is a myth. Special relativity can be developed by observing simple models. The limits imposed by the speed of light cause 5 phenomena which occur as speeds approach c. These are that 1. Objects appear to become contracted. 2. Clocks in the moving system appear to run slower than the observer's clock. 3. Time in the moving system varies along the direction of travel, with it being retarded ahead and advanced behind. 4. Observers' clocks appear to run faster than everyone else's. And 5. The one-way speed of light cannot be measured, as there isn't any way to measure absolute time or distance in a moving system. In part 1, I developed the Lorentz time transform using a hollow 3D sphere. In Part 2, the cause of the length contraction described in the Lorentz distance transforms and other questions are addressed. Because electromagnetic standing waves form the basis for many precise measurement systems, they answer the need for a different approach. Standing waves provide precise time and distance measurements in 3D in every space-time frame. First, let us examine the behavior of light in a moving system. Consider three space vessels A, B, and C, which are in a straight line, and A sends a message by laser to C via B. The light pulse travels in a straight line via B and C. If the vessels are moving and are in line abreast, does A need to aim ahead of B and C? By placing a hollow tube around the path, the light would travel down the center in both stationary and moving systems. Kinetic energy is transferred from A to the light. This is the reverse of the James-Bradley aberration. This provides a useful tool to isolate a light pulse when visualizing optical effects. This light could be a laser in a moving system. The motion of the system will automatically be compensated for, and the light would be deflected forward. The simplest electromagnetic signal is a sine wave. Here the electric field is depicted with the magnitude of the electric field shown vertically. The x-axis is distant, not time as is usually shown. If two equal signals are transmitted along the same path, and they are in phase, that is, the bumps are at the same place, the signals add and become a single signal with double the amplitude. If one signal is inverted, i.e. 180 degrees out of phase, the signals cancel to zero, and there is no signal transmitted. If the signals are traveling in opposite directions, at some locations the bumps add, while at others they cancel. The result is a standing wave. A similar effect can be seen with waves in water. In a 2D system, the waves are transmitted from the center of the cylinder and reflect off the outer shell. The result is concentric standing waves. The Doppler shift causes the change in frequency you hear when an ambulance or train passes. Here the frequency of the oscillators in both systems are the same, but as you can see, the signal from the moving source is squeezed into a shorter distance. The wavelength is shorter, and therefore the frequency is higher. We can use a pulse emitted in a 2D plane to find the Doppler frequency. The pulse of light shown as a white ring expands in a circle from the point where it was emitted by the cylindrical source. As the source and the tube move forward, we can follow the pulse down the inside of the red tube, which is set at an angle theta. When the pulse reaches the edge of the disk, we have one wavelength inside the tube in each direction. The distance from one pulse to the next is the wavelength. The wavelength from P to A and from P to B give the Doppler wavelength in both directions along the tube. The resulting equations will be used to compute the waveforms in 2D. If the velocity of the source is the same as the observer's, the transmitted signal expands spherically. Shown as a 2D slice, the waves expand out to the shell of the sphere, where they are reflected and contract back to the source. The electric fields of both signals add, interfering, and create standing waves. By slicing off part of the waveform, we can see there are positions where the electric field strength remains zero. A series of circles have been added to mark these locations. If the system is moving, the transmitted waves expand from the source, but because of the Doppler effect, their wavelength ahead of the source is shorter, and the wavelength of those behind is longer. When the signal reaches the moving shell, the frequency of the received signal is the same as that of the source. This surface now acts as a transmitter and reflects the signal, which is also Doppler shifted. The surface of the waveforms are now the mirror image of the transmitted waves. When the electric fields of these two signals are added, the result seems to be a jumble, but careful examination identifies that there is still an intrinsic pattern. There isn't any motion in the surface along the red and black ellipses. If we raise the velocity to 0.5 c, the effect is more obvious. The ellipses still sit on the surface. When the time transform developed in Part 1 is applied to this surface, it is stabilized and forms a set of elliptical standing waves which have the longer axis in the x direction. We need to interpret these results. From the reference system, the observer sees the jumbled standing waves. Because the system is passing at 50% of the speed of light, the waves would blur and look like standing waves. The vessel would be foreshortened and satisfy the requirements of the first part of this monograph. The second diagram shows the standing waves in the time frame of the moving system, but in the reference system space. The result is a set of elliptical standing waves. In the moving system, these ellipses become circles and match the standing waves in the reference system. Using the diagrams developed in Part 1, we can overlay both the standing wave patterns for the sphere in the reference system and also the standing waves seen in the moving system's time frame. They are a perfect match and confirm this development of the theory. Before we start to draw conclusions, there is one more paradox to examine. I call this the distant car paradox. Consider another planet, Blue, which is located 100 light-years away and is conveniently stationary with respect to Cat, our observer. T prime, the time there, is the same as time t for Cat. Dog is in a car on Blue and accelerates to 10 meters per second, 36 kilometers per hour, towards us. There is a stationary clock on planet Blue and another clock in Dog's car, T double prime. We can calculate the readings on these clocks using the Lorentz transforms. The velocity of 10 meters per second is so small that the square root term is almost equal to 1. We can ignore it. Thus t prime equals t minus vx upon c squared, and x is equal to 100 light years, or nearly 10 to the 18 meters, and t double prime is equal to t plus 105 seconds. The clock in the car has advanced by an additional 1 minute and 45 seconds, while the stationary clock still shows t prime equals t. There is another problem. Rat is only 10 light years from the blue planet and sees a change of only 10.5 seconds. The only possible conclusion that we can draw from this is that the effect is in the eye of the observer. The first part identified problems with measuring the speed of light and also showed it caused the time distortion resulting in the Lorentz time transform. A space transform was needed to contract the sphere, but no mechanism for this distortion was identified. There was, however, enough information to resolve the twins paradox. In a moving system, electromagnetic standing waves must also be created. These were investigated to find a mechanism whereby these do not differ from those in the reference system. The Doppler effect provides such a mechanism and explains the transforms developed by Lorentz. In the model, the transmitted and reflected waveforms are Doppler shifted, and when they are added, we have to apply the Lorentz transform to obtain stable standing waves in the moving system. The Doppler effect occurs when there is relative motion between the source and the observer, and this affects measurements made of moving objects. Thus it is impossible to measure absolute time at different locations in the moving system, as when a clock, be it electronic, mechanical or even biological, is moved, its velocity creates relativistic changes in the readings. This is the same phenomena that we are trying to measure. As in part 1 and in the car paradox, we saw that relativity is the result of distortions caused by light to the observer's measurements. The result is that every observer records that in any other system time passes more slowly and objects are contracted. On the philosophical level, one can conjecture that there could be a space-time frame which is absolutely stationary, but this would not be detectable using our available tools. Such a system might consist of a triangular mesh with each side of equal length, possibly the Planck distance. This mesh would be the ether, or using a more modern term, the Higgs field. The results do not change the equations of special relativity, but they do provide an alternative interpretation. The effect is not the result of the distortion of space and time, but an illusion caused by the limitations imposed by the nature of light. Observers are enabled to measure the one-way speed of light, that is, the absolute speed of light in any single direction. Every method measures either the time to travel both ways along a path, or relies on synchronized clocks which do not keep time when they are moved. Because the Doppler effect is only apparent when there is a relative velocity between the source and the receiver, standing waves, which are stable and spherical in the reference system, are distorted when viewed from another system. This warping can be corrected by applying the Lorentz transforms. These distortions make space and time appear distorted, but like the epicycles required in pre-Copernican times to explain the orbits of the planets, this is a mathematical fiction. The evidence for relativity, such as the measurement of the life of a muon, are as easily explained using this new interpretation. Space is not distorted. The Lorentz equations can be used to correct our observations, not to describe a bent system. The overall effect will be illuminating.